Okay, let's go ahead and get started then. So, welcome everybody to Community Research Call number 4. These are Manifold's quarterly research updates where we present progress across our projects, as well as org-related updates and any other sort of interesting or fun updates that we have for our community. Today, we will cover a brief overview of what Manifold is, and that will be kicked off by Harshika, one of the co-founders of Manifold and our technical research lead. He'll cover sort of what Manifold is, what the org structure is like, and what we do. And then we will go into some active project updates. We'll talk about some exciting new emerging directions and projects, and then we will discuss some org updates across Manifold as a whole. By the way, my name is Sid Sika. I'll be your host today, but many people will speak and present. You'll have presentations across the whole OS research team. I'm also one of the co-founders and I'm the head of operations at Manifold. And I also lead the modular space systems assembly project. So without further ado, Harsh, let's kick it off. And let me unmute you.
Okay, great. You can hear me? Awesome. Excellent. Hey, everyone. Yeah, I'll be quick with this section. I know everyone wants to hear about research updates and the meat of this stuff. So I'll just briefly motivate, what Manifold is and what we're doing at a high level, so everything else will make sense in the context of that. So we're really trying to build a new kind of research lab. In the 21st century, there's sort of this problem where different kinds of work has radically different sort of operational structures and different incentives. So you see a lot of really foundational research happen in academia. You see a lot of really focused but often applied research happen in industry. But there's also this absolute gap where very large sort of moonshot projects are difficult to fund and to operationally execute on and to achieve. Where historically there were organizations that would work on things like that. Bell Labs would be an example, or even you can consider DARPA to be sort of an organization that, or any of the ARPA style programs that support this kind of moonshot style research initiatives. And so we really want to kind of bring a lot more innovation in that space and be able to make progress on some of these really large scale research programs. And so Manifold is directly building that. And we think of this as sort of a 100-year experiment where that seems like a really long time, but it's often over those time scales that you really see the impact of both foundational and applied research take shape. And we do this in kind of a unique way. So I'll spend a few seconds on this as well. Can we go one slide forward, Sid? So our research approach is a little bit different than, whether you are familiar with sort of academic groups, you're familiar with specific industry labs, or even these kind of like new open source groups that have emerged. We try to learn and take a lot from these groups. In fact, there's been a lot of excellent work. Obviously, historically, there's been huge precedent in the sort of organizations that I mentioned. But even today, there's some interesting groups out there. You have like these AI research labs that are distributed, like Eluther, for example, that do a lot of interesting work and push the field forward. You have a lot of very large scale, well-funded private initiatives. You can even consider, DeepMind classically as one of those, or the OG OpenAI as one of those. But you also have some new wave thinkers kind of building in this space. Speculative technologies, Ben Reinhardt is an example, Protocol Labs is another one. There's a lot of these groups that are rethinking how we do research, and Manifold is kind of a novel, has a novel perspective on that. And our approach is basically to sort of both from a top-down perspective and a bottom-up perspective through the community, and we'll talk about how we structure collaborations in a second, but to basically identify these like long-standing, really important scientific goals, and to move through, we think of it as a five-phase process where we go from these exploratory projects and these research programs that you're going to hear a lot about today, where most of our projects are sort of in the first or maybe in the second stage of this process. We move from exploration to refining sort of larger top-down theses on a specific threshold event or a discrete jump in capability, technology, or science. And then to develop that into a long-term program over the course of years, and often with, anywhere from hundreds of thousands to millions of dollars in funding to be able to achieve certain scientific goals, or to realize that those are, not possible, and then to execute on those. And ultimately, a really unique aspect of it is to bring those to fruition in the real world. So, of the 1,000 ideas and research that are interesting to explore, there is also this potential chance that one or two out of 1,000 is very applicable to solving real world problems for real people. And we want to be able to spin those down and let those grow in the way that they do. And we've had some success with that so far. We can go ahead. I just wanted to give a picture of what this new kind of research lab looks like visually. We basically engage dynamically with a lot of different kinds of collaborators. We work with a lot of different kinds of funding groups, and we spin the projects that win, the projects that ultimately succeed, out so that they can grow and provide value to as many people as possible as well. And you're going to be hearing a lot about many of those projects today. Briefly, I'll touch on what does our collaborations look like. We'll talk a lot more towards the end of the talk about how you can get involved in like, a specific research project or if you have, you think there's an opportunity for collaboration. But we think of collaboration as a really important force in being able to make progress. So we have a bunch of active collaborators that we call the Manifold Advancement Network, and we really think about it as sort of an advancement network or an innovation network, where we get to work on these very focused research objectives, but we get to collaborate dynamically with the best in the field. And we intentionally have, a lot of core team members, many of whom you'll hear from today for some certain projects, driving aspects of these projects forward, but we can sort of work with the leading research groups on various aspects of the problems that we tackle. And so today, that looks like we have a fair amount of representation from some really great R1 institutions, MIT, Georgia Tech, Purdue. We also have a bunch of sort of industry collaborations as well. And that's how we're able to make a lot of progress in all these sort of varied areas. But we also are able to work towards very discrete outcomes on these large scale research programs. And beyond that, the Advanced Network is not just research collaborators, but in the event that there are particular ways that we want to distribute a certain technology, or we think that there's a really great way to communicate about it, we also have incredible people and organizations on our network to help with that. So, the full spectrum of, how do you bring a fundamental technology or a breakthrough in science, one, discover it, two, communicate about it, and three, let it get its own legs potentially and run. We try to cover all aspects of that, and that's kind of what makes us unique. So we're both highly collaborative, but in an extremely focused way to leverage things that you can only do in the 21st century to be able to lead to these threshold events or these moonshot points where we're able to achieve some massive new breakthrough. Cool. So we'll just jump into projects. That was my quick spiel on Manifold. Let's jump into it. So we have a couple of the projects at Manifold presenting today. They comprise various research directions. Yeah, I guess that's the perfect segue. So Arithra, I'll hand it off to you.
Yep. Um, yep. So, hey everyone, I'm Orithro. I'm currently a senior undergrad at IIEST in India, and I'm currently the only one working on the VLM calibration project. And yeah, so let's jump into why this is basically important and how the motivation comes for this project. Sid, can you move to the next slide? Yep. So currently, LLMs are really powerful tools in the sense that everyone's using them on a daily basis almost. Like, but the problem is we don't know where we can trust their outputs. Or, for example, uh, we ask them about a topic and they have like a very confident answer, but we then don't know how much we can trust the answer. Does the model's training data, like, is it well represented in the training data? Does it even know how to quantify that answer? And recently with these reasoning models that come up, we have a bit of a problem in understanding if the chain of thoughts that they actually produce is cohesive or not, and does it actually lead to arguments properly or not. So for example, they can show a logical flow in terms of words that might make sense to the human mind, but then dive deeper with some logic, and that's not usually true. Like we find out that they have some fallacy in their chain of thoughts or whatever. So this project basically tries to kind of figure out how much we can trust an LLM's outputs and how effectively the LLM is like LLM knows whether its own outputs are correct or not. And so We will move over to VLMs later on because this project right now is currently in a very early stage. But right now, our experiments kind of focus on LLMs and how they judge their own answers. So let's move on to the next slide. Yeah, so we have a few ongoing experiments right now, and these are we are selecting some open source models like Llama, Gemma, Quen, and then we are also selecting 2 closed source models which have their log probes available via the APIs, which are the most used closed source models right now. And we have selected a variety of data sets like GSM8K, MMLU, MED-MCQA, and SimpleQA, in the sense that we want to kind of quantify this calibration behavior, or like how well they know their own knowledge in various subsets of the knowledge field. So for example, GSM8K and MMLU kind of are on the math sciencey benchmark kind of thing, whereas MED-MCQA is a more niche domain related topic. And then SimpleQA is a more world knowledge uh, kind of thing. So whether you know some fact or not, which is like how well the fact is represented in the training data, that kind of stuff. So we do a few experiments on like how likely they are to be right, and do they even know when they're wrong. And this knowing when they're wrong is like crucially important, just so that then we'll get to figure out like, okay, this output is not trustable. So that's how we are going to, and that's why this is important basically. So we can current LLMs have these problems with like hallucinations and grounding and stuff like that, and this work ideally, the long form thing is that it's going to help in that aspect. uh, let's go to the next slides onto a few experiments that we have conducted. Yep, so these are kind of our first findings. So we see that Llama is well calibrated on GSM8K. However, the other models, and I've only shown Quen here, but Quen, Gemma, and 4.0 and 4.0 Mini are all comparatively worse, in the sense that uh, how you interpret this graph is that the more orange on the left side, the better, and the more blue on the right side, the better. But and for Llama, we can see that it's fairly well distributed, whereas for Quen, we see that even when it's right, it is kind of overconfident, or even when it's wrong, it's kind of overconfident, in the sense that like it's also predicts that its confidence probability is pretty high. Like you can see there's a huge bar on the right side of Venn graph, which basically means that when it's incorrect, even then its confidence is pretty much as the case of when it's right. So let's move on to the next slide. So this slide basically shows you what happens when asking the model on a chain of thought. So for example, the previous one was where we asked the model, okay, what's the answer to this? And then we ask it, okay, what do you think is a probability that this is like true or false? And then we collect the log probes of those true and falses. But here what we do is we ask the model how like a question, and then we ask it to figure out its reasoning and kind of think about whether it's true or false. And then finally, at the end, we ask, do you think this is true or false? And then collect the log probes. And what we see here is that there are some models that kind of back off, like Llama, which previously Llama was well calibrated, but here we can see the blue bar on the left increases, which means that it kind of backs off even when it's correct. But on the Quen side, we see a little more of doubling down, which is that it's predicting that its reasoning and thoughts are more correct. And it's more likely to think that it's correct if you give it its chain of thought. Whereas, for example, Llama says like, oh, I'm probably wrong here, and this is wrong. Yeah. So for the next few slides, we have similar benchmarks on simple QA and with zero shot and chain of thought. Simple QA is like a world knowledge benchmark, but here we can see Llama is over the board, not very confident about its answers. However, if we go into the chain of thought experiment, we'll see that Quen actually increases the performance. Sid, next slide. Yeah. Quen's Quen, on giving it a chain of thought, it actually doubles down far more, and Llama is likely to back off far more. But we don't see very well calibration here compared to the GSM 8K benchmark. So there are various kinds of facets where these models differ on different types of benchmark, and that's what basically we are trying to explore. And so moving on to the next slide, we have some current next steps that we are kind of thinking of taking in this direction, which is uh, right now we have like a pretty interesting set of results in that Llama is well calibrated on a math or reasoning benchmark, and then performs quite badly on a very simple question answer data set. And all of the other models kind of seem very worse calibrated in the sense that they are much more likely to be overconfident and like predicting that they're right all of the time. Uh, and then given the chain of thoughts, their kind of outputs drastically differ. Now, what we're trying to figure out is what kind of mistakes do they make? Do they have some consistent patterns of mistakes? For example, it could be like they have a calculation mistake that is pretty consistent across the model's outputs, or like inter-model outputs as well. So that's what we are kind of thinking of figuring out. And then we are trying to figure out if there's a certain pattern in a model family because of the way they've been trained or the training data, and like what's exactly responsible for this. So for example, if there's some patterns in factuality versus math and versus niche knowledge, and then expand onto the reasoning models and try to figure out like if we can chain, or if we can trust their chain of thoughts basically. And Anthropic has some useful work in this direction that they went to, where they said that the chain of thoughts are not exactly trustable. But yeah, we are trying to figure out in like a parallel way whether we can figure out using just the model's law probabilities, whether we can trust them or not. And then finally, we want to move into multimodality, where hallucinations is still a big problem, and figure out that, okay, whether we can just figure out from multimodal outputs what the model's calibration is on its own outputs. But yeah, that's kind of our goal with this project. And yeah, we are looking for collaboration. So if anyone thinks this project is interesting, feel free to drop a message to me or to Harsh. And yeah, I'll let Harsh take on from here.
Sorry, we have a it took a second to unmute there. Yeah, we can actually just move straight into the next presentation. I think that's from yeah, the Multinet team. So Pranav, take it away.
Hey everyone, it's nice to have all of you here. We're doing this after a while, so you probably haven't heard too much about Multinet from the team in a while as well. So Multinet's one of the projects in Manifold that's been growing both in scope, outputs, super fast. If you're already part of the Discord, you're probably seeing a lot of activity usually. And yeah, pretty excited to give you guys updates. I work on this project with Harsh, Dip, and Locke, who'll all be, speaking about their specific efforts in multinet. Yeah, we can go to the next slide. Yeah, so if you all like are in the space of robotics, VLAs, or have been paying attention to this space, you'll have noticed that in recent times, the number of vision language action model efforts has just been proliferating. Different kinds of techniques, different organizations that are attempting to do this. And for those of you who are not as familiar, vision language action models are this new class of foundation models that basically are trained or fine-tuned to do really well on vision language grounded robotics tasks. So there are a variety of techniques where like how this is approached are using like the token space of the backbone VLM or a separate action projection head different techniques there too, diffusion or a specific action tokenizer. And the only thing is that VLAs right now, they're trained or fine-tuned to do really well on very specific tasks or environments or embodiments. But we believe that this isn't the only application of VLAs. And so our thesis is that basically training a large model on web scale multimodal data and reward-based trajectories in the form of reinforcement learning or robotics data will result in this entirely new class of foundation models that are truly generalist, can autonomously plan, interact with their environments, and complete actions in an agentic manner. And we think that VLAs, can get there at the limit and, aren't really limited to doing really well on specific embodiments that you can see on this slide. We can go to the next slide. Yeah, so that's what we've been doing with Multinet. So our goal with Multinet is to build not only the largest open source vision language and control pre-training dataset for this task, but also to build eval splits that help us understand how good these models are growing into this generalist capability and agentic action-taking capability. And the reality is right now, most benchmarks, I think Aritra spoke about a few, are super specific. They evaluate certain things in LLMs or VLMs, but we're trying to build this like one-stop shop where you can evaluate the generalist capabilities of these vision language action models and state-of-the-art vision language models as well. And that's kind of what we've been doing with, if you're paying attention to our outputs, I think with version 0.1, we had a big release of our first step towards this first set of experiments that basically evaluate how well state-of-the-art generalist or vision language models or vision language action models do on, completely out of distribution action data. So yeah, you can always like feel free to like look into our website and our papers to understand, more nuanced details about what experiments we ran, the results, the analysis. And yeah, we can go to the next slide. Kind of gives you a brief about what we're assembling with Multinet. The diversity of data, ranges from all these different categories: web scale education text, interleaved image text data, object detection, image captioning, VQA, navigation-based control, locomotion-based control, manipulation-based control. So as you can see, like for a model to do really well on this wide variety of tasks and data, it's a completely different effort as compared to what is going on right now in the VLA and VLM space. We can go to the next slide. So yeah, so Multinet V0.1 was our first step towards this benchmarking effort. And you can, as you can see, the links are on the slide. You can always go read the papers and look at the website. But a brief highlight of what we did was we took three classes of models, an open source state-of-the-art generalist model called Jack of all trades by Hugging Face, and then a state-of-the-art vision language model, GPT-4o, and also a VLA, a state-of-the-art VLA, which is OpenVLA. And we basically try to evaluate all these models on a wide variety of robotics embodiment tasks from the OpenX embodiment dataset. So this expands different embodiments, different tasks, different environments, and we were basically trying to observe capability to generalize for the VLMs, generalize to the action space in general, and for the VLAs to generalize the out of distribution action spaces. What we noticed is that actually, can you go to the next slide? You can probably see the data set distribution. Yeah, so all of these data sets, different embodiments, different tasks, different environments, even like the action space itself is different, as you can see the dimensions. And what we observed is that, we can go to the next slide. I think there's some results on there. In general, most of these models perform pretty poorly on tasks like this. The one thing that we noticed was that even though all of these models perform poorly, there's specific patterns. For example, OpenVLA was already kind of fine-tuned on certain OpenX embodiment datasets, and they tend to perform really well on similar datasets, but don't really generalize well to completely out of distribution action spaces. As for jack of all trades, I think there is just poor performance consistently. Uh, uh, and then for GPT-4o, even though it doesn't like perform really well, it shows fairly consistent performance. And that's because we think it's because of a framework that we built called Genesis, where we have this specific prompt engineering framework where we try to adapt this VLM to the action space, which Dip will be talking about later. Yeah, so if you want to know more about our V0.1 results, please go to our website, look at our papers. I think it's pretty cool to see these models trying to adapt to an entirely new data set and task. So yeah, we can go to the next slide. So since V0.1, the team has been working a lot on the next step, and this is something that's completely different from robotics embodiment data. We're trying to now we're trying to work on the digital control part of it, which is basically simulated data sets. And again, these span a wide variety: navigation, locomotion, games, manipulation. You can see the data set list on our website, on the Multinet website. And another thing is that we also have a software toolkit that lets you kind of download, translate these data sets, use them either for pre-training or use the eval splits for evaluating your own models. And yeah, very easy to use, completely open source. And if you like to contribute, obviously, we're happy to take suggestions from issues. But yeah, currently V0.2 is basically these data sets that are mentioned on the slide. And our most recent effort is with ProcGen, which is procedurally generated Atari-like games, which you can see in the slide on the right side of the image. It's a discrete action space, just button presses for up, down, and variety of different actions across variety of different games within ProcGen. We've actually already started getting results and profiling models for this effort. And there's been a lot of changes with V0.2. We noticed a few limitations in our previous evaluation metrics, and we have a new set of much more robust evaluation metrics to understand better about how these models are doing. And a lot of work has gone into mapping continuous outputs to discrete spaces. With OpenX, it was much more simpler because you're adapting models that give continuous outputs to a continuous action space. But now there's a lot of work that goes into putting it into a discrete space. We've also updated the models that we're profiling on. There's been a lot more activity in the VLA space. So we've included a new family of models from the physical intelligence company. So the models are called Pi0. We'll be talking more about that in the future slides. And yeah, and just in general, the way we've adapted our models from V0.1 has improved and changed a lot. And yeah, we can go to the next slide. So yeah, like I said, I think there were a few limitations with even though we use mean squared error, a pretty standard metric to kind of understand how well these models are predicting actions compared to the ground truth actions for a given time step in an episode of data. We did notice a few limitations, especially with respect to outliers. And so we have a new updated set of eval metrics. And so Locke has actually done a bunch of work on this. And yeah, I'll hand it over to him. He can take it from here.
Hi, everyone. So we have a few new evaluation metrics for V0.2, mostly because of the two problems we now face with V0.2. One is now we're evaluating on discrete action space, and we will require a better metrics than the MSE we use for continuous action space for discrete actions. And another problem is from the V0.1 release, we realize with MSE as a metric, it can be distorted by outliers from the model's predictions, which makes sense when we're zero-shot evaluating models on out of distribution data sets, and the model has poor ideas of the characteristics of the value range and the action space. And specifically for continuous, we're now using MAE instead of MSE, which is less affected by outliers. And additionally, we also added a quantile filter to the MAE to see how the model performs more, like how the model consistently performs. And in terms of discrete action space, we're considering Breyer MAE, which because when we're working with discrete action space, a lot of times there's like Pranav mentioned, just one-dimensional action, up, down, left, right, fire or not fire. And instead of only using the action value, we extracted the probabilities over each possible discrete action value and use Breyer MAE as a better metric for essentially more information on the model's performance in discrete space. And moving on to the next, I can start talking about like our models that we are profiling for V0.2, and starting with OpenVLA. So in V0.1, we evaluated OpenVLA on out of distribution data sets in OpenX. And for V0.2, we're evaluating on ProgGen with discrete action space and also new embodiments, because in OpenX, most of the data sets were recorded from like robotic arms based robots. Also, the model also has knowledge from its Llama 2 backbone, which was pre-trained on internet scale data. And another like part of the OpenVLA architecture we have to consider is the action decoding process. So what OpenVLA does is it reserves the last 256 tokens in the Llama vocab, and then it maps into a unit for 256 beans within the range of -1 and 1. And then it uses data set statistics like mean. While for OpenVLA, it uses 99 and 1 percentiles to unnormalize the OpenVLA's data action value into the data set specific value range. It also has some manually coded rules to convert gripper command values like inverse or shift its range or binarize it. So moving on to the next slide, please. And so what we did for these to adapt OpenVLA for our zero-shot profiling in discrete space, like ProgGen datasets. First, we adapted the prompt minimally because in OpenVLA, originally it was prompting the Llama backbone to generate action for this robot. And we, in addition to like adding like the new task description, we also modify like the agent to the robot to agent in the prompt for slightly additional information on the embodiment, but keep it minimal since OpenVLA was trained with like a static fixed prompt. And the next thing we did to adapt is the action decoding process. And in order to get the probabilities needed for Breyer MAE, we essentially performed the same binning logic that was used on action values for each Llama token ID in the vocab. So to obtain a mapping between probabilities and the final discrete action values. And another thing we did is because OpenVLA is an autoregressive model, we just directly have OpenVLA only go through the autoregressive pass once to generate one-dimensional action space. We have experimented with manual physical rule transformation, such as using X and Z from OpenVLA and map them to up, down, left, right from like 3D to 2D space. However, that's not scalable to the large number of data sets we're profiling on. And additionally, it also adds manual heuristics that might cloud the evaluation. And next, I think Dip is gonna go over the next model that we are profiling, Genesis, which is our own framework, and Dip can go into it more.
Hey guys, can you hear me? Okay, cool. Yeah, so Genesis is just a fancy term to describe what we do to get GPT or any other module, VLM module, to output actions for the data sets we're profiling. And yeah, this diagram just kind of describes that. Next. Thanks. So previously, there was some great work done getting the Genesis framework off the ground and producing metrics in the OpenX dataset. And so some of what we did this time around is streamline that process to make churning through data sets a little more efficient. So in addition to profiling and ProcGen, which is a new data set for Multinet with its own challenges that you already heard about, we implemented a more modular data ingestion pipeline. So for example, we now have a base class for dataset modules, and this stuff kind of lessens the overhead work for any ingestion and evaluation for any new data sets we profile. And going with that theme, we implemented modules to use the batch API, where previously we were using singular inference, and this just makes the process less costly in terms of time and money, and also failure during the evaluation process, since OpenAI takes care of the batches once we do our job, making sure everything is good before sending the batch jobs. And we also have a more flexible prompt to where if a categorical or discrete action is detected, we ask for probabilities for each option, for each of the actions that we want predictions for, instead of just asking for the answer outright. And obviously, if it's a continuous action space, we'll assess for a value between a min and a max, as usual. And yeah, the other update is that we're using a new model, which is, it's just the normal update, GPT-4 update. But what we notice is that it is significantly worse than the previous snapshot of the GPT-4 model with the same prompt from the evals we've run. So we'll be investigating that via some prompt engineering next. And yeah, that's kind of all I had. And I think Pranav will take it from here.
Hey guys, yeah. So this is the new kind of models that we added to the profiling list for V0.2. So these are some diagrams about how the architecture works. We can go to the next slide. Yeah, so Pi0 is from a company called Physical Intelligence, and they're trying to build, I think, generalist robot policies. And their models implement action chunking, which is basically they predict a sequence of actions at any given time step. And the reason we added these two models is they're very different from the previous class of VLA, such as OpenVLA, where you had a VLM backbone and you'd reserve a part of the VLM's token space for actions, and you'd fine tune it on action data to kind of adapt this VLM to become a VLA. But I think with Pi0, the base model, it's very different, and it is a diffusion-based model. And they did this to mainly adapt it to highly dexterous and continuous control, more precise continuous control. The limitation is that zero shot, it can only produce 32-dimensional outputs because of how the action projection head is. Because of which we have to like pick one dimension out of that when we evaluate it on single dimensional discrete data like ProcGen. So makes evaluation pretty restricted, and you can only evaluate it using specific metrics like hit rates or precision recall. And Pi0 Fast is basically a one step further advancement on the Pi0 base, where they have an action-specific tokenizer. And basically for decoding, they use continuous compression methods like direct cosine transform. But one thing that we observed, we've already started getting results for some of these models as well, is that zero-shot generalization tends to be pretty bad because when they try to build something generalist, the outputs aren't restricted within a certain range, which kind of makes it hard to normalize it to whatever new data set you're generalizing to based on the statistics of the data set. And like Locke mentioned for OpenVLA, actually like the deterministic mapping between the output action tokens and the logits from the VLM backbone are much more like complicated and sophisticated for Pi0 Fast, especially because of this continuous compression technique that they use to decode their actions. But yeah, stay tuned. We're going to have results on how these models do on ProcGen and our other digital control datasets as well. And yeah, well, we already have some results up on our GitHub, and we're going to get more and probably have a detailed technical report about what we did for V0.2 and what's next. Yeah, you go to the next slide. Yeah, so just wrapping up Multinet, if any of this sounds interesting to you guys, feel free to reach out to join as an OS research scientist and, get your hands dirty, get in the arena, work on all the stuff that we're working on. But also, if you want to be like an open source contributor, feel free to like raise any issues, ways we can improve, things we can add, whatever it is. You can reach out to any of us on this slide. And yeah, happy to chat and happy to take any suggestions. Thanks.
Excellent. Thank you, Pranav, and thank you, Multinet team. I'll be presenting some updates on our modular space systems assembly project. This is our project that's swarm space robotics. So let me motivate it a little bit by starting off with the growth of the space economy. Increasingly, sort of in-space activities are becoming economically viable and valuable for reasons other than national defense or scientific exploration or scientific understanding. Increasingly, there are commercial uses of the space environment, the orbital environment, and we see that reflected in the private space economy, in particular with the sort of explosive growth that we're seeing. This figure was pulled in March of 2024. That's why the 2024 bar is not there, but really this number is growing, and the number of space companies that are focusing on areas like large structure creation or in-space manufacturing is also growing. In particular, there is a specific subset of activities that you can do in space, which is in-space assembly and manufacturing, particularly the assembly part, that has more implications for the future of space exploration and space travel. What I mean by that is if we improve in-space assembly technology, then we can assemble the infrastructure that allows us to create more in-space infrastructure and assemble more in-space infrastructure. So in other words, there's a snowball effect that will happen once we start setting up the resources and facilities that we need in orbit to increase the propagation of humanity across the universe. So this is potentially a very large market, especially the in-space construction market. It's a little bit distant in its sort of commercial implications, but the things that are enabled from the in-space assembly improvement in that technology are things like space-to-space ships, right? Like massive ships that don't ever land on a planet, so they don't need to be constrained with the rocket equation or gravitational stress, right? So they can be made very large, like a mothership kind of thing. Large space stations, right, that are permanently inhabited by humans, by scientists or tourists even. Planetary exploration, refueling stations, like these things are all made possible by improvements in space assembly technology. So we want to make this happen. But there's a specific way that we want to make this happen. Modular reconfigurable spacecraft are sort of the future, the most cutting edge version of this in-space assembly direction. What do I mean by modular reconfigurable space systems? I think these pictures kind of make it quite clear, but if we have regularly shaped modules that are swappable in their position and in their function, then we can take the same spacecraft or space structure and manipulate it so that it serves a different purpose. And this is very valuable in a unique sort of circumstance like orbit, where launch costs and operational costs are the two largest sources of cost with any space mission. Okay, so we want reconfigurable structures, and we want them to reconfigure themselves autonomously to mitigate operation costs and launch costs. And so there are sort of two main paradigms for self-assembling modular structures that have emerged. So if you have the, for now, let's assume that they're shaped like cubes. So if you have the cubes capable of thrust, then you can have them fly together into a novel configuration, into your new configuration. Or if they have some sort of pivoting mechanism, like MIT's electrovoxel project, then they can pivot on the edges. Cubes can roll over and pivot on their own edges and sort of reshape into a new shape, whatever configuration that you desire. So these are sort of the two ways that you can have modular space structures self-assemble into a new structure. The two main ways. There are other ideas. Space people tend to have a lot of crazy ideas that go sort of unfunded for a long time. But those two ideas seem to have gained a lot of traction, and for good reason. Now, you could do this in a centralized way with a sort of optimal controller, but it may or may not be well known to the audience, but centralized controllers have a lot of difficulty scaling with multi-agent systems. This is one of the main problems with multi-agent systems, is because of that factorial, right, that comes in combinations and permutations. Multi-agent systems dramatically exponentially increase or factorially increase in the complexity of their planning the more agents there are, right? So they scale poorly with n, where n is the number of agents. So if we really want large distributed multi-agent systems, if we want swarm systems, we need certain swarm algorithms, swarm control algorithms. So what does swarm mean, right? Because people use swarm to mean different things. In this context, swarm means cooperates on global objectives. It's a large multi-agent system, and the agents are only capable of local sensing, local communication, and local computation. And while if you create an algorithm that works under these restrictions, a decentralized algorithm, then it can scale to any arbitrary number of agents. And so this is the key. This is sort of what we mean when we say a swarm algorithm. Okay, so I mentioned two ways that these self-assembling modular space structures can reassemble into new configurations: flying and pivoting. And so at Manifold, we have a project on each. We have a sub-project on each. The flying cube sub-project is being headed up by me with a collaborator from Purdue named Andres. And we are working on developing a swarm algorithm for, oh, it says pivoting cubes here. It should say flying cubes, but flying cubes to reconfigure into any shape, any desired shape. And so you can see here, we have a sequence of these 5 cubes. You know, first they create these 2 lines, and then they fly together into this final structure. So this is a representation of that. So some unique challenges here are with the flying cube project, there are damage. It's very easy to damage the other cubes. You can scrape, you can collide. There's problems like that that you need to worry about. And so I would say that the flavor of this project, if there was one, is more on the dynamics and the safety. Whereas we have a second sub-project, which is being headed up by Ben. And this one is about the pivoting mode of operation. I'll let Ben take it away from here.
Hey, right, thanks. So In the pivoting cube subproject, as Sid described, it uses electromagnetic forces for each given module to pivot around a hinge rather than requiring fuel and propulsion to join each cube to the other. So this means that a given structure is at all times connected across all modules, and this introduces certain. So on the one hand, this has certain advantages to the flying cube subproblem, and on the other, it introduces other constraints. So we see that there are a couple of pivots that are allowable for a given module. So here a module can make like a 90-degree pivot, or it can pivot all the way to the other side of its neighboring module for like a 180-degree pivot. There are also a number of constraints on when pivots are not allowed. So when they would, if they were to violate these constraints, then they would collide with each other and whatnot. So any given planner that wants to accommodate these constraints would have to, or in order to accommodate these constraints, most of the planners that we see have been centralized, and they've had access to global information across the entirety of a substructure. Whereas it's likely that in a lot of the use cases for these structures, the modules would only have access to local information on their neighbors, and this would require a decentralized planning approach where each module has to make its own decisions about how to pivot. And all of these decentralized decisions across all the modules would ultimately need to result in a global effort to match a certain configuration. So yeah, this is just to reinforce the need for a swarm approach where not only would each module have a decentralized planning approach, it would also necessitate some cooperation between each given module. And well, yeah. So yeah, I want to emphasize that we are recruiting specifically for this subproject.
Well, thank you, Ben. Yes, as Ben mentioned, we are actively recruiting for the pivoting cube subproject, as well as this modular space systems assembly project in general. And we have some future projects planned in this direction as well. So there's a lot of expansion that's going to happen on this direction. So please go ahead and check out manifoldrg.com/opportunities. And we've written up a nice sort of post there that describes the skills that we're looking for. And if you fit that description, we'd love to have you on board. Okay, Harsh, would you please take it away on the emerging projects and direction?
Sure. I actually think Helen might be first. I think her slide comes first.
Hi, everyone. So thanks for being here. This is a new project we're thinking of starting, focused on probing vision language action models, or VLAs, for key concepts related to physical manipulation. So probing is the process of analyzing a model's internal representations to understand what kinds of information, like concepts or features, it has learned and where that information is stored. So our core focus is understanding how these models internally represent the concepts that are critical for robots and agents to perform actions. So while VLMs have shown impressive capabilities in connecting visual inputs with language, there's still a lot we don't know about what's going on under the hood for VLAs, especially when it comes to tasks that involve physical interactions, like picking up objects, pushing, or manipulating tools. So as for our research questions, we want to investigate first how are actions represented in VLAs, With VLMs, the research has been focused on semantic visual concepts such as object recognition and spatial reasoning. But with VLAs, naturally, we are more interested in the representation of actions. We want to probe the model layers to see whether concepts like, for example, grasp, push, or stack are encoded in a specific way, or if they emerge more holistically across the model. So second, we want to investigate in which layers are certain concepts represented. We're trying to pinpoint where in the architecture these concepts are most strongly encoded, whether they are, that's the early layers, middle layers, or deeper layers. So lastly, I just want to mention that this is a collaboration between Manifold and Tufts University. And finally, this is early stage work, so stay tuned. There will be more information coming soon.
Excellent, Helen. Thank you for that. And the other sort of upcoming project that we wanted to mention is a follow-on to the pivoting cube substructure assembly, pivoting cube structure assembly sub project, which is adaptive modular structures. So yeah, this is the next step. So the first step is let's assemble an arbitrary configuration that is desired by the end user, by the human. The second step is let's assemble a configuration that is adaptive to whatever environmental or external stimuli are present. So in this little diagram here, I have these hexagons adapting to maximize the surface area of incoming sunlight, which may be an example. But this is sort of an upcoming project that we want to start in the very near future. And you may say, well, why is this challenging? Why can't you just take the first algorithm that you develop, which is have the pivoting cubes assemble into an arbitrary configuration, and then just plug in a sort of planner, right, that chooses a configuration based on the circumstances? That would be the case if we were doing centralized methods, right? We could do that. But if it's going to be decentralized, then this problem becomes unique. It becomes challenging because now each agent needs to sort of think about the external stimuli that are present and what would be best for their swarm. And they need to coordinate somehow to adaptively configure into a novel configuration that's optimal. So we're still working on the problem formulation for this. It's not very rigorous, but there are definitely some applications of interest here, and we will be expanding into this in the very near future. Likely over the summer, you'll hear more about this project.
Okay, awesome. Yeah, thanks, Seth. So another project that we've been making some incremental progress on, and we're planning on scaling up, is at the intersection of a lot of the AI methods that even we're specifically working on and applying them to various problems within the biology sort of domain. So some of these questions are, the key sort of research questions that we're considering are, how can you build these sort of general representation learners and then fine-tune them and generate different kinds of valid biological systems? This can be at various abstraction levels from the genome to the proteome, tissue level, and beyond. What are the kinds of architectures that would do well in these kinds of problems? Biology is very complex, often hierarchical, but in a very emergent way, which just adds the complexity. And so we see a lot of breakthroughs in sort of new kinds of foundation model approaches, new kinds of reinforcement learning approaches. Generally, the trend post AlphaFold has been that AI has been very effective given a lot of data in this space, and we want to understand what other problems we can tackle. Another aspect of this is how you might develop accurate simulation environments for these very sort of complex tasks. As you can imagine, this is a huge part of, in biology, in vivo, in vitro, the notion of evaluating in realistic environments is critical to any sort of therapeutic pathway or any kind of engineered organism. And the thing about AI is that we perhaps have paths forward on being able to simulate different results before having to actually bring them to the world in the form of an actual physical study. And yeah, so these are kind of the questions that are top of mind here. We're actively recruiting for this team. This is a very early step in a very, as you can imagine, intense research program that we're putting together, where we hope to work with a lot of really talented teams and PIs and sort of experts in the field. So it's early days, but if you have expertise either in the modeling aspect, even if it's sort of more on the AI or LLM side, or as a domain expert in various subfields in biology, please reach out. We are squarely in the trying to figure out the optimal problem to pursue here at the exploratory level. So definitely reach out to me. And on top of this, we don't have another slide here, but I would also mention that keep an eye out. We have a bunch of exciting new research projects and upcoming programs that we'll be talking about and releasing more news about in the coming weeks, like on the order of like 2 or 3 weeks. So we'll keep you posted in Discord, on our website, and on our emailing list. But just keep an eye out. A lot of exciting stuff coming out. So I think that's it for future directions here. So
Yes, absolutely. Thanks, Hirsch, for presenting that. So a couple of org updates. We'll keep it brief because we're 4 minutes over, so I'll talk in double time here. But teams are recruiting, as we mentioned during each of the project presentations. If you want to get involved with that, check out manifoldrg.com/opportunities. We will be posting a ton of these sort of like job postings, or opportunity postings there. We have one up for the modular space systems assembly project, which I whipped up, but expect more to come in the near future, in the coming weeks. We also are completely open to general applications. If you want to join the OS research team, you don't have to wait for a posting that you're aligned with to show up. You can always submit a general application. We review all applications. The teams that are actively looking for collaborators right now are the VLM calibration team, Multinet, and the modular space systems assembly. But I must say that there are more. Like it seems like every project that presented is open to collaboration or is recruiting new team members of some kind. So this is not the only list, of course. Any of the projects that you heard about, please feel free to reach out if you're interested in those. There are other ways to get involved. So we've got more events coming, more CRCs, more frontiers coming in 2025. We also will start some more interactive events like reading groups and things like this. There will be some updates to the research log. We're going to make it a sort of longer form, more thought out, more thematic sort of production. So we have some sort of exciting updates there. We'll offer some deeper dives into our project as well as deeper dives into the research on like the current state of these different fields. We feel that may give more value than sort of a news update, a weekly news update. Okay, great. We also are working on a way to support many more projects that will be in the exploratory sort of phase. More on this soon. We're not quite ready to give too many details on this, but we're working on this. We're building this system out. So more updates on that coming soon. And then finally, working through the Manifold community or working through the Manifold OS research team is not the only way to work with us. We also are very collaborative. And as you have heard during this presentation, we have 3 active collaborations with MIT, Purdue, and Tufts now, which is upcoming. And so we have our Manifold Advancement Network, which is sort of our network of collaborators across the research landscape. So including academia, including industry R&D labs, and many more. If you're interested in joining our collaborator network, feel free to check out manifoldrg.com/advancement network, and you can register your interest there. And that section of the site will also be updated within the next couple of months, and you'll see all the teams and where they're from and who the collaborators are. And yeah, so if you're interested in joining our advancement network, feel free to check out that part of the site. So finally, I'd like to say thank you guys very much for attending today's CRC. It's our first one in a while, but in 2025, we've exploded off the starting block, right? We're making a ton of progress on our different research projects. The org is changing. We are really trying to improve across all of our directions. If you are interested in anything that you heard or want more information on us, you can check out our website. It's all up to date. It's at manifoldrg.com. You can email us directly at team@manifoldrg.com if you have any queries, questions. This event has been recorded and we will upload it to our YouTube channel. You can also check out past CRCs and past Frontiers talks there. If you want to attend future events, you can subscribe to our Luma calendar and you'll get notifications for any future events as soon as we start planning those. And then finally, if you want to stay up to date with Manifold, we have some socials, our LinkedIn, our Twitter, and we have a Discord community, which is very core and central to Manifold, actually. So definitely join the Discord community if you aren't there already. And then finally, we update all of our research projects, products onto GitHub, on our Manifold GitHub. And this presentation will also be shared publicly, so you guys can click any of these links. You don't have to like write them down by hand right now. We will share the link to this. Yeah, so thank you guys very much for attending. And Harsh, if you had any final words?
No, yeah, thanks everyone. This is awesome, and we'll have another one coming out in another. We do these every quarter, so stay tuned, and we'll be sharing these slides and things as well. Excited to engage with the community more and push forward. So thanks for your time. Have a great weekend. Take care.
Thank you guys. See you all.